Dear all, good morning. Now our lecture is orthogonality. This lecture we are going to discuss what is the orthogonal of vectors, orthogonal of subspaces. Fundamental theorem of orthogonality. We'll see first of what is the orthogonal of vectors. The definition: let V be an inner product space. An inner product space. The vectors comma V belongs to V are said to be orthogonal. Or that means, or you can say U is said to be orthogonal to V. That means the inner product is 0. That is U transpose V equal to 0. Generally, I take a standard inner product. U transpose V equal to 0. Any two vectors are orthogonal means the dot product is, that means U dot V equal to 0. The dot product is 0 vector. Suppose we take suppose this set. Suppose any set. This time we take taken only two vectors. Suppose any set U1, U2, Un. That any set is orthogonal. The set is orthogonal means if Ui comma Uj, the inner product is 0 for I 1 less than or equal to not equal to j less than or equal to n up to n vectors. That means they are mutually orthogonal. That means mutually orthogonal. Every vector is orthogonal to remaining vector. So U1 is there, it's orthogonal to U2, U3, every vector. U2 is there, orthogonal to U1, U2, U3, every vector. That means mutually orthogonal. The set is called orthogonal set. We will discuss orthogonal set in next unit. Orthogonal set and orthonormal set. But time being, we require what is the orthogonal vectors. Orthogonal vectors means the dot product is 0. Now orthogonal subspaces. What is the orthogonal subspaces? So two subspaces, U and V, any two subspaces, a vector space, any vector space, are orthogonal subspaces if every vector U, suppose I am taking every vector U in U, is perpendicular to every vector V in V. Suppose I take a vector in U, a vector in V. So these are two subspaces. This orthogonal means U perpendicular to V. Orthogonal. Orthogonal means the inner product is 0. This one. Now observe here the orthogonal vectors. So take 0 vector, 0 of U. All U belongs to V. You know this inner product is 0. That means every 0 vector is orthogonal to every vector. You know. So you take 0 vector in this one. 0 is orthogonal to every vector. Means 0 is always orthogonal to vector. So in a subspace, suppose same vector. Suppose one vector is there. Suppose V belongs to U. Same vector V belongs to V. Same vector is orthogonal means V transpose V equal to 0. Orthogonal. When it's possible, the same vector is orthogonal means must be 0 vector. 0 vector. I mean 0 vector itself. This is subspace means 0 vectors must be there. 0 vector is orthogonal to every vector. Suppose same vector is orthogonal means that must be 0 vector. So take some example. Suppose take U equal to 1 minus 1 2 and V equal to 2 0 minus 1. These are orthogonal or not? Now observe here are orthogonal. Means suppose take U transpose V or U dot V equal to now dot product 1 into 2 minus 1 into 0 0 into minus 1 minus 2 equal to 0. So they are orthogonal. Suppose asking like find x, suppose x1 y1 z1 and x such that x is orthogonal to 1 1 1, orthogonal to suppose u1 and u2 1 minus 1 0. Find a vector x such that x is orthogonal to u equal to this vector and u1 and u2. How to find this one? How to find? See, now here is given x is orthogonal to u1 u2. Given x is orthogonal to u1 and u2. What that mean? That is x into u1, that inner product is 0, and x into u2 also 0. Now that implies for the x into u1, the inner product, the dot product of x and u1. That means we get x1 plus y1 z1 equal to 0, and x into u2, inner product of x into u2, dot product 1, that way 1 into x1 minus y1 equal to 0. Now one free variable is there, that implies from here you can write x1 equal to y1, and suppose take 1 2, and from 1 substitute x1 equal to y1. That means z1 equal to, suppose we are taking one free variable to take x1 or y1. x1 equal to, suppose write y1, x1 equal to y1 or y1 equal to x1. That means we will get z1 equal to minus 2 y1. And therefore x equal to, x is x1 y1 z1. This is equal to, now substitute what the x1 is, y1. Oh, no. x1 is y1 is a free variable y1, z1 is minus y1. Whatever you take that vectors, suppose you take x1 equal to y1, or you can take x1 equal to y1 or y1 equal to x1. You get different one. You take y1 common, this is a 1 1 minus 2. What is the y1? Y1 is a variable, y1 belongs to a real number, that is spanning. Therefore x equal to 1 comma 1 minus 2 is orthogonal to u1 and u2. You can check it. That x1, u1 into x, 1 1 minus 2 0, 1 minus 1 0, that's minus 0. That means this vector is orthogonal to u1 and u2. So this is the way to find orthogonal vectors. Yeah, any two vectors are orthogonal means that is the inner product is 0. The 0 vector is always orthogonal to every vector. So you take any in a plane, in a three-dimensional x, y, z. So we'll take any line in the plane. Just imagine in a three-dimensional. So we take any line. If you take any plane that is passing through origin, it is always orthogonal to the line vector. Now you can observe your room. Yeah, one line. The plane is, suppose you take roof. That is the plane. Now take line. That is orthogonal to the roof. Orthogonal means they are making 90 degrees. That means the line is always orthogonal to plane. It's passing through origin. Next, already we studied 4 fundamental subspaces. Suppose if we take AB on M by N matrix, null space and the row space, they are orthogonal subspaces. Row space and null space are orthogonal subspaces. So already we know row space and null space are subspaces of R power n. Remember one more point, note. This is the dimension of, suppose W1 and W2 are subspaces V. The dimension of W1 plus dimension of W2, it's greater than dimension of V. In this case, the subspaces are not orthogonal. That means if any two subspaces Subspace or subspace of some vector space. The dimension is not more than dimension of the equal or less than, maybe orthogonal, but it's more than is there, not as orthogonal subspaces. Are not orthogonal subspaces or not orthogonal subspaces. Remember this one. The dimension must be not more than space. Okay. Now we'll see this one. Null space. We already know null space means solution set of x equal to 0. That I give idea. Solution set of, we look at this solution. Look at x equal to 0. That means solution set. If where A is the M by N matrix, now M by N matrix means you have to write rows. Suppose it's row 1. How many rows are there? Row 2. Rows. Row n. Because it's M by N matrix. And you get x vector equal to 0. See now observe here. See that means row 1 vector into x vector. The solution set x. X means x1, x2, x. That solution 1 is equal to 0. Now you can observe here. Row 2 into x equal to 0. And so on. Row m into x equal to 0. That means each row, that how many independent vectors are there? Independent rows. Each row is orthogonal, the dot product is 0. That means each row is orthogonal to null space vector. That's why null space and row space are orthogonal subspaces. The row space and null space, these are orthogonal subspaces. So now observe here, what the dimension? Suppose if dimension of row space is R, what the null space of dimension? N minus R. These two are subspaces of R power n. What the dimension? This one R plus n minus R is equal to Rn. Equal to n only. This R cancel. Not more than. That means these are orthogonal subspaces, or you can say orthonormal subspace. Not orthonormal, say orthogonal subspaces. Orthonormal will discuss later that topic. Orthogonal subspaces. So, suppose example, the rows of A is, suppose I am taking 1, 2, 3, 2, 4, 6. So 1, 1 minus 1. Sorry. Rows. The rows of A are orthogonal to null space. How many null spaces are there? This is a 2 by 3 matrix. The null space, how many vectors will be there? Will be possible? Only one vector, 2 rows. 3 minus 2. 1. This is I did mistake. Better text. This is not a independent vector. I have taken 2 multiple. That is dependent. Only one vector like. Orthogonal to null space. Okay. Okay, this one. These are independent. Orthogonal to null space. X equal to 1 minus 1. These rows are orthogonal to this one. Check it. Ax. What the Ax? A is the 1, 2, 3, 3, 4, 7. Now x is 1, 1 minus 1. Now multiply this one. 1 plus 2, 3. 3 minus 3, 0. 3 plus 4, 7. 7 minus 0. This one. These are linear. This I taken dependent. That's not correct. It must be independent. Independent are from a row space. Dependent vector not from a row space. Suppose you are taking dependent vector, the row space is only one vector. In that case, null space contains 2 vectors. That is the one. Next, what about column space? The null space, left null space. Null space of any A means left null space. The left null space of A and the column space or orthogonal subspaces or power m. Already you know this column space of A and the left null space transpose subspaces of R power m. So now if you already know the fundamental theorem, the dimension of row space column space is A of A equal to A column space of R and the left dimension of left null space m minus R. What the sum? R plus m minus R is equal to m equal to space Rn space. That's why they are orthogonal. Now the proof is simple. Similarly, you can observe A transpose x equal to 0. X is the solution set of left null space. Left null space. Okay. Now A transpose. What the A transpose means? It's, okay, for example, you can observe suppose A11, A12, A13, 3 by 3 matrix. A22, A2, okay, 2 by 3 matrix. Now we have to discuss rows. The matrix is orthogonal to say x equal to 0. This is the solution of solution set of x equal to 0. This is orthogonal just now we discussed. Now row space. Now A transpose. What A transpose means? A11, A21, A12, A22, A13, A23. This A transpose, it's again it's 0, the left null space. A transpose x equal also 0, the left null space. Now A transpose, what is it? This one? Column. What's the column of A? This is the column 1 of A. Column 1, okay, you can take column 1 transpose. We are taking A, column 1 transpose. Next we get column 2 transpose. Up to how many columns are there? You have 2 by 3, 3 columns. If m by n columns, how many columns? N columns. Column n columns. This is the n by m matrix. So take x equal to 0. Now when you multiply column 1 transpose into x, you get 0. This multiplication. And so on. Column n transpose into x also 0. That means each column is multiplying with this null space vector, it gets 0. Means left null space is orthogonal to column space. But left null space is orthogonal to column space. If you take any example, suppose we have take left null, suppose you can take previous example, find that left null space. Now you can check it. That is the orthogonal. Now already we discussed these 4 fundamental subspaces. Already I have given exercise also. Now you can check it. They are orthogonal or not. It must be orthogonal. If it's not orthogonal, they are not a row space, not a null space. If you find out row space and null space exactly, the row space, null space must be orthogonal. Similarly, column space and left null space is orthogonal. This one is not only orthogonal, this one, it's more. Now observe here, row space and null space. Suppose we are getting row space, null space, the total dimension will get full space. That's why it's not only orthogonal. Suppose we take R3. Suppose we take R3. Suppose take 2 lines, any 2 lines. Okay, dimension of each line is 1 and 1. But when you are adding the sum, it's equal to 2, but it's not equal to whole space. Lines means subspaces of R3, not equal to not whole space. Now, means the lines, it could not be row space or column space, or row space or null space. It could not be row space. So you take matrix. Suppose you take any matrix. Suppose it is 3 by 3 matrix. You are finding row space or column space or null space, whatever. We are finding row space. space dimension is 2. So dimension of row space of A is 2. The dimension of null space must be 1. When you are adding 2 plus 1, we get equal to space. That means these are called orthogonal complements. Yeah, that's what the definition of orthogonal complement. Means when the two subspaces of that space, sum of dimension equal to whole subspace, yeah, one subspace is orthogonal complement of another subspace. That's the main thing. Now definition. Let S is subset of an inner product space V. The orthogonal complement of S denoted by S. This pronunciation per consists of those vectors in V that are orthogonal to every vector U belongs to S. What are the vectors are in S pair? The vectors are orthogonal to every vector in V. Every vector in U means this vector in V. That means S pair B equal to V belongs to V. Every vector in V comma U. The inner product of V comma U is 0. Whatever you take vector, suppose I am taking V vector in U. So you have to find S pair. S pair means suppose set contain like U1, U2, U3, some vectors are there. This vector is not in S. Suppose this S pair means whatever you take vector in V, this vector must be orthogonal to every vector in S set. The set is called complement. Those vectors are orthogonal. This vector is only orthogonal to one vector. That vector is the S pair. I will see. Yes, some in particular, a given vector, one vector U belongs to V, we have U pair B. The word orthogonal. U pair means any vector V belongs to V comma U inner product is 0. Suppose what are the suppose we take one vector. Those vectors are orthogonal. The vector set is U pair. Yeah. So suppose U pair means only vector. Oh, suppose this vector is orthogonal to which vectors? It's the orthogonal pair. One theorem. Let S be a subset of a vector space. We already know this is subset. Not only subset, it's a subspace of V. S pair. See a subset that S pair is subspace of V. Already you know subspace means you have to satisfy vector addition and scalar multiplication. Suppose it's clear, you know clearly 0 belongs to S pair. Why? Because it's 0 vector. We know 0 vector is perpendicular to S means you have to use orthogonal. Line means perpendicular. Vector is orthogonal. This vector is orthogonal to every vector. Means 0 vector is orthogonal to every vector. One vector is orthogonal to every vector means it's in S pair. That means clearly 0 belongs to S pair. Now let what I am taking was U1 comma U2 belongs to S pair. Subspace means it must be satisfied the vector addition alpha U plus U2 belongs to S pair. If you prove this one, our aim is done. That means it's a subspace. Vector addition and scalar multiplication. Now, for any scalar, alpha belongs to F field, any field, and so take you have to prove this is a complement of S set, and U belong suppose take V belongs to S. Now you have to prove in S pair means the vector is orthogonal to this vector. Our aim is you have to prove this inner product alpha U1 plus U2 comma V. The inner product is 0. Inner product is 0. Alpha U1 plus U2 belongs to S pair. Now this by inner product definition, this one can write alpha U1 comma V plus U2 comma V. What that means? Alpha into U1 comma V. U1 belongs to S pair. V belongs to S. S pair means this vectors in V also. Whatever this is a subset. The vectors in belongs to V also. When that belongs to V, one vector is in the U pair U1. V is S. V also in vector space. Clearly, u1 I am taken S pair. V belongs to S. V vector is also in V. Small v vector is also V. But we are taking S pair means orthogonal to every vector in V. Capital V. If one of the vector in capital V means this is the 0. Orthogonal. Similarly, this is also in V vector. If u2 in pair B means this is orthogonal to every vector in V. So 0 equal to 0. And therefore, alpha u1 plus u2 belongs to S pair B. Hence, S pair B is a subspace of V. This is the proof. Not only subset, what are the S pair B is there? Subspace. Set of all orthogonal vector to S subspace. For example, uh, let W is subspace of R4 and spanned by the vectors 1 comma minus 1 2 3 transpose. We take u1 u2 equal to 0 1 2 minus 1. Okay, whatever take belongs to R4. One. Yeah, this is W is a subspace of R4. It's spanned by these two vectors. Now, find find the orthogonal complement W pair. Yeah, just now I told you when that orthogonal complement means this W and W part, the some dimension of W and W part that must be equal to space. A space dimension is 4. Space dimension is 4. W dimension 4, but subspace of W is spanning by two vectors means dimension of 2. The dimension of W pair, the orthogonal complement must be 2 because the sum is must be equal to space. In that case, they are orthogonal complement. And we will see solution to find this one. See, they are given it's a subspace. W is a given W is spanned by u1 and u2 vectors. See now we need to find the orthogonal complement. We need to find vectors. Suppose we take common variable. Okay, right. V equal to we take x, y, z, w transpose belongs to W pair. And vectors such that that means V is in W pair means that V, the inner product of V into U1 is 0. You can say orthogonal to every vector space because in the vector in R4, but it is subspace of the R4 subspace W. It's spanned by this U1 U2. Vector in parable, this is orthogonal to every vector 0 and V comma U2 also 0. What that mean? V comma U1. V this one, U1 is this one. Now that dot product, inner product is x minus y plus 2z plus w equal to 0. So take this one and v w2 u2 v u2 this one x is 0 y plus 2z minus w equal to 0. Now solve these two equations. You can go for any method. It's a two equation better to adding these two equations. Adding 1 plus 2. What we get? When you are adding y cancel x plus z minus 2z w. That means x equal to minus wz minus 4z minus 4z minus w. This is the one. Now two free variables are there. Now substitute in this one second equation or first equation, whatever. Better to substitute in from 2 w and z and w is there. Z and w, y is there. Now y is equal to, right, w minus 2z is equal to okay, there is no x, no? Okay, sorry, substitute in x, substitute in one equation, 1 equal to y equal to, substitute in 1, substitute in 1 minus 4z, okay, substitute in 1, when I substitute in 1, x equal to, generally 1 equal to, from 1 y is equal to minus 2z minus 3w minus x. Now substitute x value. When you substitute x value, minus 4z plus 4z minus 2z is z minus 3w 2w minus w. So now we got x y z, xy value, and z and w are free variable. Therefore, v, what is the v spanning? X y z w. What spanning what vectors? X is minus 4z minus 2w. Y is z minus w. Z and w are free variables. That means if you take z common, minus 4 2 1 0, take w, minus 2 minus 1 0 1. Yeah, this one v is belongs to w. This v is spanning by two vectors. Spanning z comma w, any real numbers spanning. Yeah, these two vectors spanning w pair group. Yeah, therefore the vectors, okay, minus 4 2 1 0 transpose, minus 2 minus 1 0 1 0 1 or 2 1 transpose are basis, or a basis for w per w per. These are basis. You can check it. If any doubt is there, it must be orthogonal to each vector. Now check first vector w1 and this first vector. 1 into minus 4 minus 4 minus 4 minus 1 into 2 minus 2 minus 4 plus minus, okay, right, 1 into minus 4 minus 4 minus 1 into 2 minus 2 2 into 0 0 plus 2 into 1 2. I did any mistake? 1, okay, let's take it, x minus 1 2z plus 3w, y 2z minus w. Okay, when you are adding this one, y cancel, x plus 4z minus 2w. Okay, x equal to minus 4z minus 2w, x equal to minus 4, y is equal to 2z, right, these are plus, y is equal to 2z plus 3, this plus only. Okay, but plus means we'll get this of mistake. We'll see that one. You can project that. Suppose they are not orthogonal, we did some mistake. Yeah, I did a mistake some. Okay, we'll see. Okay. Now that is correct. Y is equal to 2z plus w plus x. Now add x. 2z minus 4z minus 2z, w minus 2w, w plus x. That means, okay, sorry, we are adding x only, not x. Yeah, this one. Now here minus 2z sorry, x is minus 4z minus 2w, y is minus 2z w. That means we get minus 4 minus 2 1 0 minus 2 1 0 1. The vectors are minus 4 minus 2 1 0 transpose minus 2 1 0 1 transpose are from a basis for W pair. Now you can check it. Vector 1 into minus 4 minus 4 minus 1 into minus 2 plus 2 1 into 2 2 3 into 0 0 is equal to 0. First vector orthogonal to first vector. Now again first vector orthogonal to second vector also, you can check it. Minus 2 minus 1 minus 1 minus 1 plus 1 minus 1 2 into 0 0 plus 3 into 1 plus 3 minus 3 plus 3 0. Similarly, this second vector also orthogonal to each vector. That's why this is the orthogonal complement basis W. It's the way to find. Okay, suppose it's given only W is a subspace of R4. It's spanned by only one vector. One vector. The complement of W is contain three vectors because sum of subspace and complement subspace equal to space dimension. If one vector is subspace is spanning only one vector, the complement is spanning three vectors. Suppose it's a subspace W is spanning three vectors, the complement is spanning only one vector. Now, fundamental theorem of orthogonality. What is the fundamental theorem of orthogonality? Null space. This is already we discussed this orthogonal complement of the row space because dimension of what the dimension of null space plus dimension of row space equal to total space. That's why null space is orthogonally complemented to row space. That means null space orthogonal complement, that pair is row space, or you can say row space, that pair is null space. This is a fundamental theorem. Similarly, left null space, dimension of A transpose, nullity of A transpose, rank of column space or dimension of column space. This column space you can write the same as R of A. Sorry, you write A. R of A. This is equal to, we know M. This is the R, this is M minus R, we get M. That means null space of A transpose the same as the column space of A, or you can say column space of A pair is null space of A transpose. That means the null space always orthogonal to row space. The null space, left null space is always orthogonal to column space. This is the main thing. This is the fundamental theorem. Already we proved this one, orthogonal complement. The dimension is equal to same. That means it's complement. Null space is orthogonal to column space. We know the first fundamental theorem of linear algebra. Dimension of null space, dimension of row space equal to the sum is n. But dimension of R of A is R. This is n minus R. We get same. That means it's a complement. Orthogonal complement. This is the one. Now see this figure. Dimension of this is a row space, column space, null space, and we got orthogonal. That means they meet at zero vector. A zero vector in each space is there. The row space and null space meet at zero vector. Same as column space and left null space meet at zero. There are orthogonal that make angle 90 degrees. Now each vector in row space it's mapped to column space of B vector. There X is split to XR XN. XR is the row space vector, XN is the null space vector. When I write AXR, it goes to B vector, AXN is goes to B vector. AXN is goes to B vector. What is that right? Suppose any two vectors are equal. Suppose XR, XR prime. There are two vectors in equal in the rows. What about the subtraction xr minus xr prime? Equal to zero vector. The same vector is in row space means zero vector. That means it belongs to null space also. That means this xr minus xr prime belongs to null space. When you take axr minus xr prime is equal to axr minus xr prime. That means axr goes to b, xr prime also goes to b. This is equal to 0. That means this belongs to in null space. Yeah, this is the one. We know row space dimension are this one. That means we know dimension of row space and column space is same. But that means every vector in the row space is same as mapped to column space vector. Same vectors. That one. One vector is mapped to same one vector, another vector. That means every vector is mapped to same, one of the vector in column space of A. If three vectors in row space is there, those three vectors map to again three vectors in column space of A. Similarly, null space map to left null space. These are not same dimensions. If n minus r, this n minus r. Okay, now I am stop here. Thank you. Yeah, I am writing. I am giving two or three examples. Exercise. Write in notes. See the notes after watching this lecture. See the notes. I will give two or three examples.